Hello everyone, and welcome to the 11th lecture of AAE 301. In the last lecture, we've looked at an alternative way to describe a system, which is called the state space representation or state space model. In addition, we learned how to derive the transfer function of an LTI system from its state space model. In this lecture, we will learn how to do the opposite, which is to derive the state space model of an LTI system from its transfer function. First, let's consider an LTI system described by a transfer function g prime of s. We say the state space model ABCD is a state space realization of g prime of s if the transfer function associated with the state space model is equal to g of s. Here, the transfer function associated with the state space model ABCD is given by C times the inverse of Si minus A times B plus D. And the derivation of this result is discussed in lecture 10. And now let's look at an example to help you understand the concept better. In this example, we will be given a state space model, and we will check whether this model is a state space realization of the transfer function g prime of s of the mass spring damper system. Okay, for a mass spring damper system with system parameters mass m equals to 1, damper constant c equals to 0.5, and spring constant k equals to 1, its transfer function g prime of s is given by 1 over s squared plus 0.5 times s plus 1. And here we are given a state space model with system matrices A, B, C, D shown here. And it is claimed that the model is a state space realization for g prime of s. In other words, the transfer function associated with the model is equal to g prime of s. And now let's verify this claim together. The transfer function associated with the model is given by g of s, which equals to c times the inverse of si minus a times b plus d. Next, if we substitute the matrices A, B, C, D into this expression, we will get g of s equals to 1 over s squared plus 0.5 times s plus 1, which also equals to the transfer function of the mass spring damper system g prime of s. Therefore, we can conclude that the state space model ABCD is a state space realization of g prime of s indeed. Later, we will look at a systematic way to obtain a state space realization of a proper rational transfer function g of s. Before that, let's review the definition of a proper rational function. We say a complex function g of s is a proper rational function if g of s can be expressed as a fraction of two polynomials, n of s over d of s. And the degree of the numerator polynomial n of s cannot be greater than that of the denominator polynomial. Furthermore, note that any proper rational function g of s can be expressed as a sum of a strictly proper rational function g naught of s and a constant d. Here, a strictly proper rational function is a function that can also be expressed as a fraction of two polynomials, only that the degree of the numerator polynomial is strictly less than that of the denominator polynomial. As an example to illustrate this fact, let's look at the function g of s equals to s squared plus 2s plus 4 over s squared plus 2s plus 1. And notice that this function is a proper rational function because it is a fraction of two polynomials, and the degree of the numerator polynomial is the same as that of the denominator polynomial. Next, if we divide the numerator polynomial by the denominator polynomial, the result will be a sum of the strictly proper rational function 3 over s squared plus 2s plus 1 and the constant 1. Okay, now let's delve into how to derive a state space realization of a proper rational transfer function g of s. Step 1. Rewrite g of s as a sum of a strictly proper rational function g naught of s and a constant d. Since g naught of s is a strictly proper rational function, we can express it as a fraction of two polynomials, where the degree of the denominator polynomial d prime of s is n, and the degree of the numerator polynomial n prime of s is at most n minus 1. Here, the constant d is the direct transmission matrix of the state space model that we are looking for, and the function g naught of s is equal to c times the inverse of si minus a times b. Step 2. To find the matrices a, b, and c, we define the functions g1 of s as 1 over d prime of s, and g2 of s as n of s, and rewrite g naught of s as a product of g1 of s and g2 of s. In other words, we will view the system described by the transfer function g naught of s as a cascade of two systems described by two transfer functions g1 of s and g2 of s. Note that the input to g1 of s is u of t. The output of g1 of s, which is the input to g2 of s, is denoted as y tilde of t, and the output of g2 of s is denoted as y prime of t. Next, to obtain the matrices A and B, let's first focus on the transfer function g1 of s. By the definition of a transfer function, g1 of s is equal to y tilde of s over u of s, which equals to 1 over d prime of s. Here, y tilde of s is the Laplace transform of y tilde of t, and u of s is the Laplace transform of u of t. Now, if we multiply u of s on both sides of this expression here, then we will get y tilde of s times d prime of s equals to u of s. Next, by applying inverse Laplace transform on both sides of the equation, we will see that g1 of s is the transfer function associated with the system described by the LCC ODE shown here. Now, the matrices A and B can be obtained by deriving a state space model for this LCC ODE. And to obtain a state space model for this LCC ODE, let's recall what we have learned in lecture 10. Essentially, we can easily obtain a state space model by collecting the coefficients of the LCC ODE and filling them into the matrix templates. Specifically, a state space model for the LCC ODE associated with the transfer function g1 of s consists of the state space. Specifically, a state space model for the LCC ODE associated with the transfer function g1 of s consists of the state dynamics equation x dot equals to ax plus bu, and the output equation y tilde equals to c tilde times x. Here, the state x is an n vector with each state variable xi defined as the i-1 derivative of y tilde, and the system matrices A, B, and C tilde are summarized here. Next, to obtain the matrix C, we focus on the transfer function g2 of s. By definition, g2 of s is the fraction of y prime of s over y tilde of s, which equals to the numerator polynomial n prime of s. Here, y prime of s is the Laplace transform of y prime of t. And now if we multiply y tilde of s on both sides of the equation, we see that y prime of s is equal to n prime of s times y tilde of s. Next, by applying inverse Laplace transform on both sides of the equation, we can see that y prime of t is simply a linear combination of the derivatives of y tilde of t. And now recall that each state variable xi is defined as the i-1 derivative of y. Therefore, y prime of t can also be expressed as c times x, which is a linear combination of the state variables. At this point, we have obtained the matrices A, B, and C, which are the system matrices associated with the state space model for the system described by the transfer function G0 of S. Specifically, the state transition matrix A is an n by n matrix consisting of three components. A n-1 by 1 zero vector, a n-1 by n-1 identity matrix, and a 1 by n row vector comprised of the coefficients of the denominator polynomial d prime of s. The input matrix B is a n by 1 vector with all components as 0, except for the component on the last row as 1. The output matrix C is a 1 by n vector comprised of the coefficients of the numerator polynomial n prime of s. In addition, the state space realization ABCD obtained by this procedure is a minimal realization of G of S. If you want to know more about this, you can refer to page 33 of the slides. Now let's practice what we've learned with an example. Specifically, let's derive a state space realization of the transfer function of the mass spin damper system we've seen earlier. Recall that the transfer function G of S of the mass spin damper system is given by 1 over s squared plus 0.5 times s plus 1. And now let's derive a state space realization of G of S together. Step 1. Rewrite G of S as a sum of a strictly proper rational function G0 of S and a constant d. Here, G of S is already a strictly proper rational function, so G0 of S is equal to G of S and the constant d is equal to 0. Step 2. Derive the matrices A, B, and C by comparing the coefficients of G0 of S. Here, the degree of the denominator polynomial is 2, so the number of state variables n is equal to 2. Next, by collecting the coefficients in the numerator polynomial and denominator polynomial of G0 of S and filling them into the matrix templates for the matrices A, B, and C, we get A equals to the matrix 0, 1, negative 0.5, negative 1. B equals to a column vector 0, 1, and C equals to a row vector 1, 0. Now we have obtained a state space realization ABCD of the transfer function G of S, and the matrices ABCD are summarized here. In addition, this realization can be described by a block diagram shown here. The part highlighted by the yellow marker is associated with the state dynamics x dot equals to ax plus bu, and the part highlighted by the green marker is associated with the output equation y equals to cx plus du. From this block diagram, we can see how the state variables and the input are related, as well as how the output is related to the state variables and input. Specifically, the derivative of the state variable x2 or x2 dot is equal to negative 0.5 x1 minus x2 plus u. And the state variable x2 is simply the integral of x2 dot. And the state variable x1 is just the integral of x2. On the other hand, the output y is equal to x1 plus 0x2 plus 0u. Okay, this is the end of this lecture. I hope to see you in the next one.